So what we're going to do, I think, is hopefully today I'm going to wrap up chapter 4 on the introduction of the device and some small analysis on circuit part. So what we're going to basically do a little review on what has already been discussed on Tuesday, which is we start understanding the basic operation principle of bipolar junction transistor. As I said, for active, anyway, these are all for active, during active mode. So only active mode will we be building these models, and both the large signal and small signal. So these are the models we established. So there's this large signal. The top is for the large signal, and the bottom is the small signal. The yellow part is the part I will typically refer to as we call the first order model. Typically, when we address or analyze a situation, not necessarily for device, but this is very, very often used when you analyze a circuit or you analyze a device. First, or you look at for example, a virus under microscope. What you do is that you start by finding out where it is. So this is the same thing, is that when you view a device, what we want to do is you capture the main behavior of the device. So this first order is simply describing the main operation or the main component which construct the current in your system. So that's what we call the first order model. So you want to capture the gist of how it functions and its basic operation, the key parameters or key behavior direction. So once we have the larger picture, then you look in. So these white things, you see these? These are when you look in. And you see like, oh, there's not only, for example, for coronavirus, you see like, looks like a round thing. But that's the yellow model. So, but when you look in, zoom in, and there's spikes and stuff. So there's details in the virus. That's the same thing. And when you look in, it's not a virus, but when you look in, you see details. So these details will then give you additional information as to when you operate under a certain mode, these details will count, or these details will have significant impact on its behavior. Okay? So as I said, we already introduced the first order BJT model and the small signal. These are typically referred to as the hyper pi model, and the reason that is why the number that the pi comes about. So you see, there's a definition on changing the voltage, the resistance between B and E as R pi, and the voltage across as V pi. So this will also give us the naming convention, which will give us this. So today we're going to address additional, I wouldn't say too much into second order analysis, but the non-ideal factor when this current source is no longer ideal, which means that it's no longer simply a current source, there's other dependency, which would then introduce this called output resistance. So this actually come about because of what we call the early effect. So we're going to discuss secondary effects and its impact. So early effect would then lead to a non-ideal voltage control current source. This non-ideal current source then would then introduce a finite, we call it finite output resistance. So this would then lead to the introduction of RO. And then this is the only thing we're going to address as the second order part. These parts, these other parts, these are parasitic resistance RB, RE, RCs, and also there's parasitic capacitance C pi C mu. We'll discuss those when we talk about frequency response. So when we discuss how fast the transistor can transit, then these would then count. But if you're only looking at, if you're ramping your transistor at a very slow speed, whether they are carrying a bucket or not doesn't really make too much a difference. But if you're considering speed, then these buckets would then would then delay the speed of the operation. Okay, so what we're going to do today is then we're going to first start by these. This is also still inactive. So all of the above are talking about devices, especially NPN transistor in active mode. So these are also only valid when a device is operating in active mode. So the second thing we're going to do, of course, we're going to spend a little time. I don't want to spend too much time on those non-active mode, but I'm going to spend a little time talking about the second thing I'm going to talk about is saturation, of course, a little bit. When you operate in saturation, what happens? And of course, we're going to talk about a little bit on why. I already mentioned a few times that when you operate in reverse active, you get poor performance. I'm going to tell you why. And then finally, again, I'm going to spend a little time on, hopefully, we'll be able to save some time for PMP. The reason why I didn't start with PMP, there's also a reason, because it's not very good in performance. So we're going to talk about that as well. These two are the same because they're not in terms of performance, they're poor. Therefore, it's not that critical in most of the amplifying circuits. You won't pick a poor transistors, or if there's a choice, you definitely put the high performance one rather than the poor performance ones. So we're going to talk about that a little bit, okay? So as we already, I'm going to start by giving an example. So let's say we start by testing the transistors, the output characteristics. We start with looking at the output characteristics. So if this is my output current, I'm looking at, as I said, one of the testing conditions is that you want to look at if I'm applying different output voltage, what is its corresponding output current characteristic. So this is very important, the output characteristic of a transistor. So instead of having a voltage control testing system, another very commonly used testing system is by injecting current. So I could, instead of having the voltage, I could then set a different IB. Okay? So this would then give me a better control because I know that the collector current and base current has a constant ratio. So if I'm doing this type of testing or measurement, what can be expected will be a curve looking something like this. So this is very, very commonly used, or if you see pictures or characteristic of a technology or transistor, these are the typical characteristic curves. So if you look at VL versus VO, so here VO is VCE, right? And IO is IC. So if I'm injecting a constant step of current, for example, if I'm ramping this, not ramping, just set it at different level, for example, sorry, at 0, let's say 1 microamp, 2 microamp, 3 microamp. I'm just going to inject 3 conditions. So what we would expect is that the current, if I'm injecting 0, I'm expecting that there's no current. 0 corresponds to 0. So this is IB equals to 0. And then if I increase it, I'm expecting this would then rise to IB equals to like 1 microamp. So I should be able to get something more like a equal step because I'm injecting the same amount of beta, right? Same step in the increment of base current. Sorry. I'm stepping the base current. Okay? So if I'm doing this type of test, I could actually reflect this. This gives me 0.3 milliamp, 0.2, 0.1. If I give you this plot, you should be able to tell me what is beta. What is beta? What is beta? The typical number we have already used. What is beta now? 100, correct. So now just by measuring this, that's to say if you have a transistor, you want to know its beta, this is the setting you want to use. Okay, so this would then also tell us that this gives us beta of 100. This is what you would expect if you have a device with a beta of 100. For example, if you bought a device to give you the spec that this device has a current gain of 100, then you should test it under this setting. Okay, so this we already discussed. And one of the issue is that one person called Early, his last name's Early. That is why Early, in fact, it's not, Early, in fact, doesn't really, the Early is the name of the person. So one person started measuring this type of characteristic, and then he found that this is what you expect. But what he actually measured doesn't look like this. It looks something more like, let me use, where's my, okay. So the real measurement, so let's say the green is what you expect. But then in his real measurement, it looks something more like this. Instead of having a flat line, so let me first set the boundary. Let's say this is my VBE. So I know that past this, I should be able to observe that this is inactive, right? So we know that inactive, based on our first order model, I should be seeing an ideal current source, meaning that the current will be set by base current under, so IC should equals to beta IB. So if I give you a constant current at the input, you should get a constant current at the output, which is independent of output voltage. But what happened is that this Early person, he found that his measurement results indicate that the curve looked more like this instead. So green is first order, and this is the real measurement results. If you actually get a device, so we assume that the green is what you project based on the model. So based on the model, it tells us that it's supposed to be an ideal current source, but it's not an ideal current source. So what he did was that in the maybe 70s, he doesn't actually spend much time in understanding what happened. But what he did is that, how do I actually use this in my circuit? How does that impact my circuit? I want to model it. So he used this most, I should say, pure experimental method to do a curve fitting. So his idea of model this non-ideal characteristic is this. So he then, let me redraw this again. So let's say if you're Early, and then you found the curve looks something like this, right? So the story is that this person found out that it's no longer a flat. Let me redraw this. I'm not doing a very good job. So let's say this is the measurement results of this person. And then he found that it's no longer a flat line. So the idea is then, if I'm measuring IC versus VCE, what happened is that it will then no longer, if I'm using the above model, which will only depend on VBE, it will no longer reflect the real collector current. So the idea is then, I'm just going to do a simple extrapolation. So his idea is that I'm just going to do an extrapolation of the line. So as I said, there's no physics in it. We're going to discuss the physics a little bit, the reason why it looks like this. But what he did was that, how do I project, or how do I model this characteristic? So the basic idea is then, I'm just going to do an extrapolation, and then luckily, these curves then coincide to each other and give a voltage which is defined as VA. So VA is typically referred to as the early voltage. So I'm not talking about Y yet. I'm still talking about what has been observed and how does this person solve the problem of providing a more refined model. So the way of providing a more refined model is then it's very, very rough. I'm just saying that he's using a rough model, but this is very useful when you have a rough model, meaning a simple model. It will then allow you to do other projection into circuit application much more easy. So we're not going to go into the detail as to what happened yet, but just to tell you then how he solved the problem. So he wants to refine the model. So remember our previous model is IC equals to IS exponential VBE over VT. Okay? So this is my original model. But the original model will give you the green line instead of the yellow, right? So you want it to more closer to the yellow line so that your prediction will not be off too much from the ideal model. So he added the correction terms. How does one add a correction term? So the idea is very simple, is that I'm assuming that this level is very similar to this current level is very similar to this current level. There's only a very small little gap. So there's a, as I said, this is a VCE set. So first of all, if you do the measurement itself, you will see that this VCE set is typically very small. So meaning that this voltage, this current at this level and this level is very similar. So what he did is that he used this current, assuming that they're the same. So this would then be this current, right? So he will then get the projected level. So the projected level will be the slope. The slope would then be IC, I should say. I'm just going to explain what happened. So the plus will be the flat line. And he added a correction term. How does one add a correction term? Meaning that the additional VCE, if you add additional VCE, it would then project it by the slope, which is IC over VA. So using this, I should say, let me rephrase this. So the way to do this is that I'm correcting this term by, so I'm assuming IC, the real IC is IC without correction. So without correction plus a delta I. So how does I project the delta I? ICO will be the same. This is the ICO. This is the ideal model. Right? So how does one project delta I? So delta I will be determined by the slope. The slope is this. I'm using the slope to project additional VCE. How does the additional VCE increase the slope? So slope is defined by ICO. It's not Q. ICO simply means that there's no the ideal first order model divided by VA times VCE. So he simply used this height to develop the slope and use the slope to project further down when you move to the, when VCE increases. So let me just write down. So your corrected current will be, once again, ICO plus a delta incremental IC. So this will be, I'm assuming that this is flat, and this difference is delta IC. So this referred to ICO, right? I'm using ICO to project the slope using the additional VCE to project further downwards. Okay? So then I'm just going to write down the equation. This is IS exponential VB, still the independent VCE part plus the dependent part. So you're using ICO. I should just write ICO. Actually easier. Sorry. So based on this equation, this is ICO plus ICO VA, VCE, right? I'm just summing these two up. Sorry. So this would then give me ICO 1 plus VCE. Okay? So finally, our equation would then become my original BE dependency and then plus VCE dependency. So the refined model would then tell us that the collector current will be both affected by VBE and VCE. And the main control, of course, is still VBE because VBE is an exponential. So it has much, much stronger control on the overall current. But this would then still come in to lead to a small increment in current. Okay? So this is just the derivation of the model we're going to use. And how does that impact our small signal model as well? We're going to talk about that a little bit. But before we go into that, does anyone know why? This one just, so the whole discussion is that this person observed this, and then he just established a model and then refined the large signal model by introducing this correction term. That's basically what we already talked about. But why? Why? So I was trying to answer last week, I think last time. A student asked me that I asked a question as to why is it flat? First, you ask yourself, why is it a flat line? And then you revisit why it's not a flat line, right? So you start by asking yourself, the reason we assume it's flat is because I know my current, if you go back to the physics, the IC is the emitter current diffusion. Did I make a mistake somewhere? No? It's the diffusion current in base. In base. Okay, so it's supposed to be proportional to dn dx, the rest. So meaning that if you look at what happened, physically what happened is that if I have a BE junction, once again, BCE. There's a 4-bias PN junction. So that I'm saying, I'm going to tell you that this will look like this, right? So this is my electron dn dx. On the left-hand side, what determines dn dx? Once again, this is on the pinpoint, your dn dx would depends on 2 points and the width, right? So your triangle, the slope would defined by the triangle width. And then these 2 points. If I'm reverse bias PN junction, as I said, our previous understanding is MP at WB and MP at 0. This will be MP0 exponential VBE. That's how the exponential VBE come about, right? And this is approximately 0. So you basically have the 3 points. The height, the difference, and the difference is fixed by VBE. And when you apply more bias, reverse bias, for example, if I'm increasing VCE, the problem of increasing VCE, what is VCE? VCE is VCB plus VBE. So I know that if my VBE is fixed, the increase of VCE, this is fixed, right? I'm assuming my base are fixed at for example, the turnout voltage maybe 0.8 volt. And I'm starting to ramp this, meaning that this would then imply your VCB increases. This is the reverse bias voltage, right? This is the reverse junction. So your VBC junction reverse voltage. Which is the VR of the reverse bias PN junction. So as VR increases, what do you expect? This is already 0. You can put it down even further, but this doesn't really make too much difference. 0.1 or 0.001 doesn't really make too much difference in this linear projection. So what it does is that it will actually increase what? Remember the triangle, there's a depletion here. So I have depletion, right? This is the NA, this is ND. I have ND plus NA minus, right? So if I'm increasing this reverse bias PN junction, what do you expect? The depletion region will grow. Okay, so depletion will widen. So the key words is that it's going to be increase, so widen depletion. What does it mean is that I have a junction right here. Let's say this is my junction. This is the place of my junction. It will then deplete further down this way. This will also deplete. So it's like the vacuum in the back expand further to the front. So what happened is that you will see your depletion growth a little bit. We didn't talk about this before because we didn't actually count the depletion at the beginning, at our first order. Just look at the first order behavior. But now if you zoom in, you will see that these depletion will grow, especially when the base width is small. If my base width is like 100 micron, I don't really care if it inches in a little bit. But if my base is only 0.1 micron, any inches would then affect something we call, instead of having a physical WB, we then need to have to define something called this is called the, let me use another. WB effective. So there's an effective WB. There's discrepancy between the effective and the real WB. So what is an effective WB? If you define this as X, we use our previous, this is down to minus Xn. And I'm sorry, this XP and this X. This point will be X equals to Xn. If I'm setting this to 0, then this will be X plus Xn. This will be minus XP. So your final effective width. So what happened is that once again, as VCE increases, under a fixed VBE, your VCB increases. It's mainly when we increase our output voltage or collector voltage, what happens is that your depletion region grows. The growth of depletion region will then lead to X. The depletion region grows a little bit. So then what happens is that your WB effective, and it says WB, I'm just going to roughly say that it's defined as WB minus XP, will then decrease. So this would then lead to an increase of what happened. Therefore, this is a more hand-waving way of talking about why you see this rise of current. This is because this is called, either there's two names for this. Either it's the early effect because the person early observed this. So typically referred to as the early effect, or another name is called the base width. This is more modulation. So this will give you the cause of why. So either way, these two are these are talking about the same thing, because as the base being modulated, your vacuum or the pump is pushing forward, or the extent of this pump being pushed forward, then the distance for the minority character travel reduces. Therefore, it would then lead to an increase of collector current. Okay? Is it good? That is why, as I said, in the first order model, if I have a very, very wide base, what happens is that I will see a flat line because any additional depletion, I don't actually see too much depletion, and the voltages drop on where? I'm trying to answer the question. The additional VCE, VCB, the reverse bias voltages drop on BC junction. So if the growth is very limited, if I have a wide base, I don't actually see too much of a difference. And it still pinch my MB and WB close to 0. That is why you see a flat line. Only when the effective distance changes, you will see the effect seeping up under the early effect. Okay, I'm just trying to say that additional voltage is being dropped on the depletion region. So the depletion region will eat up the voltage. But when it has effect in narrowing down your base, then you wouldn't see the effect, an early effect, or the base width modulation. So it essentially reduces the distance between the diffusion of 2 points. Okay? So the next thing I want to talk about is then, okay, so this is the thing we already have our model. What is this implication? The most significant implication, other than projecting your DC current, you have to do a correction, meaning that maybe a 10%, 20% correction in the output current level. So I have the correction term, right? 1 plus VC over VA. This is not the key impact on the overall behavior. The key impact is actually at the output resistance. Because if you think about it, what does output resistance suggest? It suggests that, let me draw this. If I have an ideal current source, let's say if I have an ideal current source, this is what happened IC versus VCE. Right? So this simply implies that if I'm applying in the small signal domain, if I'm changing my collector voltage, meaning that if I'm modulating, let's say this is the same thing. This is VC. And if I'm having a small little VC changes, if I really have a flat line, what does it suggest? It suggests that it will not. So if I'm doing this projection, what is the delta I? If it's a flat, this would simply suggest that the delta IC is 0, right? If I'm applying a small little difference, let's say this is my VCE, O. I say quiescent point. I'm moving a little bit on the right, moving a little bit on the left. If I have a flat line, it would simply say that I would then have a flat line. A flat line would suggest that even though I move around, the current will not change, right? Because of the flat line. So this would then equal to 0, and this would then suggest something we refer as an output resistance. We define something called the output resistance. If you define your output resistance, small signal output resistance, as 1 over DI, where IO, remember this is IO, this is VO. Okay, if this is the case, I know since my denominator is 0, this will simply give me infinite. for ideal current source, right? Because this is an ideal current source. An ideal current source will give me infinite output resistance. My output resistance is infinite because the delta VIO is 0, even though I'm changing because it's flat. So now it's not flat. So then we typically refer this as a finite output resistance, because if your RO is infinite on this model, you would then, because it's infinite, so that the resistance is infinite, then it's open circuit, right? So now because of early effect, we no longer, so we have to refine our model. If you ignore early effect, even though I have this RO, because RO is infinite, you can simply skip that because it's open circuit. But now it's, because of early effect, you have to have what we call the finite, instead of infinite, you have a finite RO. So now the model would then consist of 3 parameters instead. Let me just first highlight this V pi. So then I have 3 parameters, R pi, GM, RO. Okay? So instead of 2, then the model needs to expand to include output resistance. As I said, output resistance is defined as the inverse of the change when I modulate this. This is how you test it. You modulate from your initial point and then look at what's the corresponding changes in your output current. And it turns out to be 0, therefore it's infinite. But if we consider early effect, then the curve will look something more like this, right? The real curve will be the yellow one. Okay? So if this is the case, what happened is that when I do the same exercise, when I'm wiggling around from my operating point, it would then reflect a small little delta I. So delta IC is no longer 0. So that's the very, very important difference. Because in previous case, if we don't consider base width modulation effect, because of the flat line, you don't actually need to include this in your model. But now, because the finite resistance, it would then need to be included, and it has significant impact on determining transistor amplification factors. So that is why it becomes much more significant other than this DC correction. The correction on DC current would then affect your accuracy of your current, but this would then tell you the limitation as to the amplification of a circuit. Output resistance is very, very important. So what is the amount of output resistance? As I said, if you look at this, what is the output resistance? You could do it through the equation itself, or we can do it just simply when early model this. You simply model this by the slope, the inverse of the slope. So if I'm using the model, you can do it through the textbook, but we can actually, you can use that, you can insert that refined model into here and then get your output resistance. So RO, once again, by definition, is dV the inverse of this. I'm simply going to insert that, and that will give me something VA over ICQ at ICQ. So you simply do the derivative and get that result. Therefore, wait, did I get it right? Inverse, there's an inverse in that. Therefore, your final results, let me write it in the right. So the RO would then become VA over I. Your reference, all the small signal parameters will depend on your quiescent point. So ICQ. So once again, let me summarize the refined small signal model. I have GN, which is ICQ over VT. I have R pi, which is inverse GM beta. And then finally, output resistance is also dependent on your biasing point as well. Okay? And this is very, very important. This would then limit your ultimate gain. We're going to talk about that. Ultimate performance of the transistor or technology. Okay? Good? Any questions? So having the basic understanding of this will then help us move on to the. Oh, this will conclude all the DC. If you're discussing DC circuits, or not, I should say, we're not considering parasitic capacitance effect. As I said, we're not talking about frequency responses. Then this is the model you need to use. We're going to follow these models for follow-up circuit analysis in chapter 5 as well. But then before we go to chapter 5, there's still a few loose ends, as I said, number 2, 3, 4, on devices we haven't addressed. So I would like to spend probably the next hour also talked about these issues. So we're going to go back to device physics, and just to give you a brief introduction as to what happened during saturation, reverse active, and a little bit on PNP transistors. But I want to emphasize once again, in the following discussion, we'll mainly focus on these type of models and these analysis and the small signal models or large signal models for the follow-up discussion. We're not going to talk, you're not going to actually use too much, not really care too much about the 2 and the 3 because if you're actually setting your device the wrong way, then your circuit may be in saturation or in reverse active. But if you're operating in the right direction, it should be at active mode and follow all these guidelines in analysis. Okay? So even though I'm saying that it's not that important, it's still interesting understanding why or what happened during these, if you're operating in this mode, these modes. Okay, so what we're going to do is talk about saturation. Saturation happens a lot more frequently than reverse active. Reverse active, you need to just connect your zeros and your upside down. It's more like an upside down problem. The saturation can happen fairly often in the circuit, even when you're designing a amplifier. So we're going to talk about what happened. So what defines saturation is that when VBE and both junctions are 4. So based on these curves, these analysis, it will happen here, right? So this will be, this version is actually, we call the saturation version. If you, in your output characteristic, where we identify the saturation is that this is when VBC is also BC is larger than 0, right? Because this is BCE, so if it's smaller than this, if your VC is smaller than this boundary, then this would then 4 bias PN junction. So you 4 bias both junctions. So simply what happened is that if you look at this plot, I'm going to draw the plot. So let's say if this is the emitter base collector junction. I'm just going to draw the junctions. And then what happened is that if you think about it, I'm going to use the red. I would then have two 4-bias p-n junctions. So let's say I'm still having VBE slightly higher than VBC. In most cases in saturation, even though one is 4-biasing, but this one is 4-biasing a little bit more, this is less. So if this is higher, for example, I'm just going to give a number. Let's say this is 0.8, and this is maybe 0.1. So let's just look at the scenario. So what happened is that, let me draw the line and explain what I'm trying to say. So if this is saturation by definition, this is active. We know that the boundary is VCE. We know that this is VBE. So let's say I'm fixing my VBE at 0.8 volt. I'm trying to reduce my collector voltage to lower than 0.8. So this is the line. This is the measured response. Let's say this is IC versus VC. I'm trying to explain what happened. Okay? So if I'm sipping down here, let's say if I'm at this point, 0.1, which is, this is already 0.8. So at 0.1, what happened is that originally we have this slope, right? So this is what happened when you have high NP exponential, I should say NP at x equals to 0 at a very fixed 4-bias condition where it's controlled by VBE, right? So this point doesn't change because my VBE is fixed. But on the left-hand side, what happened is that you start by raising this a little bit from 4-bias this junction. So this will then be raised a little bit. But what happened is that if I'm only at 0.1, which is, for example, maybe 0.7 volt, if this is the 0.7 volt point, the way to think about this is that even though I'm raising on the right-hand side, but because of the exponential term, so this is the NP at WB. We're not considering modulation effect. So this will be NP0 exponential VBC. Okay? So what happened is that first, we need to recognize that it will raise whatever, you now start to pump a little perfume from the back. So you're raising your minority carrier concentration at the collector side as well. But even though that happens, because the exponential, if you use the number, this is 0.8, and you use 0.1, there's a significant difference between the two. So this will then lead to something if VB's, I should say, if VBE is still larger than VBC, what happened is that NP0 is still larger than NP at WB. Now, as you say, you don't actually see the raise when it happens. Okay? So only when, so let me just write down. So dn, what you can actually do is that do the exercise on your own. So dn dx becomes WB exponential both sides VBE. So it's a competition between the two 4-bias. NP0. They open, let me NP0. So you will see the rise when it's close enough, meaning that if you're actually closer, for example, you're closer to maybe 0.4 volt. At 0.4 volt, which means that the difference between the two becomes 0.4, so that you actually see the difference. Therefore, you see the small, you start to see the drop. So at 0.2, for example, 0.2 maybe when BE minus BC. Typically, when it's smaller or equal than 0.4, NPB over NP0 becomes significant. This is simply because of the exponential. What I want to say again, this is because of the exponential nature of the thing, the potential exponential dependency on its minority carrier concentration. Therefore, if it raises a little bit, if there's large difference, you don't actually see the impact. When it raises to a certain level, what happens is that this would then raise to here, for example, will be more flattened at 0.2. So this is at 0.2. So then you see significant difference in the gradients. Okay, so this is one impact. Another impact is, have you thought about what happened to the base current? During saturation, this junction doesn't change, so I'm still having to support this diffusion current IH in emitter. But if you think about the collector, what happened at the collector? The collector will be forward biased as well. When the collector is forward biased, it will be higher. It will be something more like this. So what happened is that even though the collector is pretty wide, but to a certain extent, this level, the N, the P N0, that collector, I want to say this. Let me write it here. Pn0 at collector will be much, much larger than Pn0 at emitter. Right? Why? Why do I draw this big chunk of hole current, holes in the collector? Because collector is much more lightly doped. Remember the level. Let me just give a number. This is a typical numbers. This is 10 to the 19th. This is maybe 17, and this is 16. So this is how much? 3 order of magnitude lower in its doping concentration. So I'm just trying to emphasize that this is because NC is much, much lower than NE. Therefore, you would then have a lot more minority carrier concentration when you forward bias. So it's very costly. What happened is that the most significant thing other than the drop in collector current is the raise of base current. So what happened is that you will then see significant raise in base current because my base current, IB, will then has to supply both sides in the emitter and the collector. Both the emitter, let me use E instead of, in both the emitter and collector. Collector. And this will be much, much larger because we didn't suppress it with heavily doped structure. Okay? So you will see a lot of minority carrier coming in, and you have to supply both sides. So your base current would increase significantly during saturation. This is one of the 2 effects. Once again, reduce the reduction of gradients is one of the key feature of in saturation is the raise of minority carrier concentration at the back when we're pumping electrons from the back. The other thing is that you would then have significant raise of base current because you're forward biased both junctions. So you need to supply both. And this will be much more significant because emitter has been deliberately suppressed. The whole current has been deliberately suppressed because I heavily doped this. This is deliberately done. But this is a side effect we can avoid. Okay, so let's take a break for 10, and we're going to dispense the quizzes.